Okay. Thank you very much, Professor Lev, to invite. Well, what I'm going to talk about is, up to now I have seen many people talking about symmetry. But sometimes break the symmetry is also something quite interesting. So the idea is to see the spectrum of quantum rings under tilted magnetic field. So usually people take the ring and consider the magnetic field perpendicular to the ring. Now we're going to take the tight magnetic field, so we have another degree of freedom. So we don't have to change the parameter, but we change the angle, so consequently we change the, we break the symmetry and change the Aharonov-Bohm oscillations. So the idea is to consider this ring, and the magnetic field has an angle, and we used to consider gallium arsenide in this quantum ring, and we solve the, basically we consider this magnetic field, and we can solve, we consider the Zeeman effect also, and we solve the three-dimensional system, not real two-dimensional. And the main reason is that if you consider just two-dimensional, eventually you can have in the Hamiltonian one term that depends on this term here, but you cannot neglect this. If you consider just the first order, you look for the Hamiltonian on the inside the plane, you keep this term that's yeah. You can still, oops. And we shown that if you consider up to the second order, these two terms, they will cancel. And so depends on the gauge that you use, you can have, let's say, when you go to the limit of two-dimensional, you can have wrong results. And what we do, basically, we use the same method that Andrei used on the other poster. He used a propagation in real time. Now I use the propagation in imaginary time in order to get the energy levels. And the good thing about this method is that we can use any kind of geometry and any kind of potential. Even if you have roughness, you can propagate your wave function. And here you can separate the equations in the spin part and the space. And then we solve the equation, consider with spin and without spin. And we can see here the split if you have high magnetic field. Here you have two heights for the quantum rings against the magnetic field. And now we consider two different angles and see what's happened when we change the field. From these dot lines, you can see that we change the period of the Aharonov-Bohm oscillation. And, well, some more results, you can get more details. But this is quite interesting because when you go to theta, to the plane, we go to this real, let's say, known effect of the magnetic field. And it's quite different from some results that have been obtained, consider, let's say, some gauge operator. Okay, here's the conclusion. So thank you very much.